Talk about here regarding linear functions, some characterizations here. Okay, when we deal with a linear function, which again is the one we've probably had the most experience with, okay, talking about it from a verbal point of view, we can call it a polynomial of degree 1. Okay, so if it's linear, it has degree 1, that's the highest powered term. Okay, so it still qualifies as a polynomial, it'd be a linear polynomial. Okay, algebraically, we have several different ways we can write the function. If we want to write it in terms of y, or f of x, if you will, though, we're going to need everything on the same side. Okay, so therefore, point-slope form, we would need to transform that a little bit. Okay, the best bet here is to write it in y equals mx plus b form, so we can see the slope and see the y-intercept. Okay, all right. Graphically, as we talked about, it's a slant line with a slope m and a y-intercept of b. Okay. Okay, and then analytically, a couple things to analyze a linear function is that if we have a function with a constant non-zero rate of change m, then the function is increasing if m is greater than 0, okay, and decreasing if m is less than or equal to 0. Okay, and then the initial value, which is really just the y-intercept, is always going to be that b value. Okay, so key issue here again is that if m is greater than 0, in other words, we have a positive slope, okay, we should expect the line to be increasing as we go from left to right. Okay, if the slope is negative, less than 0, then we should expect that the line go down from left to right. Okay, we have a negative slope. Okay, and that would be really the only analysis here regarding linear functions. Now, one of the things that I do want to add to this, though, is that there's a couple things that we generally want to find when we deal with lines. Okay, so if I had some random line like negative 2x plus, let's say, 8, for instance. Okay. One of the things that I might want to find if I want to graph this, okay, I could certainly make an XY chart and plot whatever points I want to. I can pick whatever x's I choose and plot enough points to graph it. Okay, however, sometimes, and this is true for really all equations, okay, when we want to analyze it, we want to find the intercepts. Okay, we of course know that the y-intercept is already in front of us when it's in this form. It's going to be 8. But think about why that is. If I want to find the intercepts in any capacity, whether it's a linear function or not, okay, if I want to find the y-intercept, I'm going to put a 0 in for x, okay, and solve for y. Because if I'm on the y-axis, my first coordinate had better be 0. True? So if I plug a 0 in here, I'm going to get 0 plus 8, which is 8. Okay, if the equation is solved for y already, it's generally pretty easy to figure out the y-intercept, isn't it? Okay. Now, what if I want the x-intercept, or as we know with parabolas, there might be more than one x-intercept. That means we're going to put a 0 in for y, because if we're on the x-axis, okay, that means the y-coordinate would be 0. So in this particular case, if I were to put a 0 in for y, I'd have a 0 equals negative 2x plus 8. And if I added 2x to both sides and divided by 2, I could get my answer of x equals 4. Okay, so the x-intercept of this particular line would be 4, 0, and that would give us 2 important points that are on the line. Okay. This procedure right here, could this be used for any kind of function besides linear function too? Okay. If I want to find the y-intercept, 0 has to be the x. True? So in general, if I had to say that in words to somebody, what would I do to find the y-intercept? I'd plug in 0 for x, and I'd solve for y. If I want to find the x-intercepts, I'd plug 0 in for y and solve for x. Okay? And this general strategy can be used for any kind of function. Now, are they all going to be as easy to solve as a linear function? No, not necessarily. Okay. But keep in mind that's kind of our theme in finding intercepts. Okay. All right.